Hi folks, and welcome back to Physics with Captain Rod here. I'm making this video to just be kind of an introductory video here about the mathematical relationship between electric fields and electric potentials. So, taking a look at this picture, we're going to imagine that we have, we got some sort of coordinate system, an electric field, and for the sake of this example, we'll assume uniform, has some sort of magnitude plus I direction as represented by this electric field vector. We're going to talk about some things about here, position 1 and position 2 here in just a moment, but before we get to that, let me talk about the equipotentials. So, if the electric field is uniform, then we would have an equipotential that would look like this in this picture. Right? And I might call this potential 1. And it's not just a line, it's actually a plane. This would come at you as well. And anywhere on this plane here, we would be at the same potential. And then if we move over to here, I can draw another equipotential that goes through position 2. And we might call that like potential 2. Actual numerical values do not matter. We could call this one 0, in which case potential 2 would be some negative number. We could call this one 0, and potential 1 would be some positive number. I'm getting my plus and minuses based on the electric field direction. Remember, electric potential always decreases in the direction of the electric field. All right, so let's talk about now calculating the potential difference. So potential difference is field strength times distance. But the electric field component you use has to be in the direction of the distance. So I usually put something like this, E parallel to D times D. I usually talk about this just in terms of magnitudes here. And then what I do is say, well, if you are downstream of the field, so to speak, you are moving towards lower potential. When you move the other way, you're moving towards higher potential. But what we're going to do here is we're going to write this again using this delta x here. So we're going to have E times delta x. Now if we imagine going from 1 to 2, that's a drop in potential. This is and that means that this delta V should be negative. This E is a magnitude, and the delta x is positive. In this picture, I'm going from left to right. So what we'll do here is I'm going to put a minus sign here. This equation now is good. You tell me a delta x, given our electric field, I'll tell you the change in potential. Including the sign. If delta x is positive, it means we're moving to the right, and then the change in potential is some negative number. If delta x is negative, it means we're moving left, right? And then that needs to be an increase in potential because we're moving into the field, and you'll notice a minus times a minus is a plus. So this equation is good now, either direction. Now, notice if we solve it for the electric field, what we get is delta V over delta x with a minus sign. And now if we imagine delta x going to 0, or we imagine like limit as delta x goes to 0, the delta x becomes a dx. It becomes infinitely small. So what we have here is a derivative relationship. The electric field is equal to minus dV dx. Now, first of all, let's talk kind of generics here. What does that mean? Tell me the electric potential if you hit it with a position derivative, right? You take a d dx, and now you know the electric field. If we arrange this, this reads dv is equal to minus e dx. And now we can calculate the difference in electric potential via an integral relationship. Because if I integrate the left-hand side, we get delta V. I'm just going to write equals minus integral e dx from, we'll just say position 1 to position 2. So the relationship between the electric potential and the electric field is a calculus relationship. Tell me the potential, I'll take the derivative of it, tell you what the electric field is. Know the electric field, integrate over a change in position, e dx, and you get the change in potential. Now, this was in a one-dimensional sense, but this is true in 3D. Let me talk about what these relationships look like in 3 dimensions. Notice that this electric field is in the direction of this delta x here. In a more general sense, we can write this same relationship here. I'm going to put sub r here, which means electric field r component, where r is just some arbitrary direction here. I'll put r hat here. Would equal minus dV dr, meaning Whoops, that's not a vector. Sorry about that. Didn't mean it to be. Whatever the potential is, differentiate it in a certain direction with respect to position. Of course, with a minus sign, you get the electric field in that direction. Rearranging this slightly, all right, so dV is going to equal minus E sub r dr. Now, before we integrate, let's talk about this a little bit more. So E sub r dr basically means this. Here in this picture, we have an E in the electric field vector. E sub r is the component of that electric field in the direction of r, whatever that happens to be. And this expression, you know, this was a dr here, then becomes a dot product here. So we can write this dV is equal to minus E dot dr in the language of vectors, because E dot dr is magnitude of E, magnitude of dr, cosine of the angle between them. But the E cosine theta, that's what this is right here. That's the projection of E, the electric field vector, in the direction of r. And then the difference in potential is then the integral of this expression, minus E dot dr, from position 1 to position 2. So again, the intention of this video here is just to be a quick video to introduce the relationship between the electric field and the electric potential. And again, this is important stuff here because it's very imperative that we be able to go back and forth. You know, finding electric fields and electric potentials are pivotal to the understanding of electricity and the mechanics of electricity. So again, it's a derivative integral relationship. If you know the electric potential, differentiate it with respect to some direction, that gives you the electric field. If you know the electric field, integrate across position, E dot dr from 1 to 2 tells you the difference in potential. So anyway, again, this is just meant to be an introductory video about the mathematical relationship between the electric potential and the electric field. Have a great day.